The management of access controls on datasets has to satisfy multiple objectives, from protection of proprietary data to provision of read access to public data to imposition of right restrictions. There are potentially a very large number of communities whose access may need to be controlled. Standard examples include project members. Team members typically have access to all datasets and are able to both read and write. Collaborating project, participants from other institutions may be granted tickets that provide access to specific datasets. Data grid members, data may be shared directly with persons who have a data grid account. Federated institutions, federation enables persons with accounts in other data grids to gain direct access to data. External public, datasets can be given anonymous access for persons without a data grid account. The mechanisms that control access range from access controls within the data grid to tickets for external access to federation of data grids to establish trust between multiple data grids. Across all of the types of access control, mechanisms are needed to group users into communities that have similar access rights. An example is the iPlant Collaborative with potentially 30,000 users. Projects self-organize around small teams of about 5 persons per team. To keep the number of access controls to a minimum, groups of users are formed. The access controls are granted to each group. To automate setting of access controls, the microservice MSI set ACL with parameters flag, permission, account, and path can be used. For the communities that have been identified, the controls used to manage access include project members, use account name or group access controls, collaborating project, use tickets, data grid members, use public access control, federated institutions, use account name and group access controls, external public, use anonymous access permission. The Microservices Workbook, IRODS 4.0, lists examples of the use of each microservice. For the MSI set ACL microservice, the input parameters are recursive flag, a string either default or recursive. Recursive is only relevant if set with access level set to inherit. Access level, a string containing one of the following permissions, null, read, write, own, inherit. Username, a string, the username or group name who will have access controls changed. For usernames in a federated data grid, use username pound zone name. Path name, a string, the collection or data object that will have its access control changed. All of the input parameters are strings. An example of the use of the MSI set ACL microservice is shown here in the DMP set public.r rule. The rule is available in LifeLive Zone, Home RW More Rules, DMP set public.r. The rule has an input parameter, relative collection, which defines which collection will have access controls changed. The rule creates the full path name to the collection by prepending $rodzone client, home $username client. The collection name is then checked for existence. The MSI set ACL microservice is called to turn on inheritance on the collection. This automatically sets the access controls of files deposited into the collection to be the same as the access controls of the collection. The rule also turns on read access for the anonymous account, enabling access by persons who do not have an account in the data grid. Take 7 minutes and complete exercise number 80. For your research collection, set access permissions on a file for another person in the group class 624. Set public access, the anonymous account, on another file. Please load a paragraph describing your result into the lifetime library in the subcollection class INLS 624 by the end of today's class. The Tokai to Kamioko Neutrino Experiment, T2K, is a high-energy physics experiment in Japan that has international collaborators in the United Kingdom. The Nobel Prize in Physics was shared by Takaaki Kajita and Arthur MacDonald for the discovery of neutrino oscillations. This observation proved that neutrinos have mass. The experiment required the management of data from distributed sources as well as the analysis by a distributed team of researchers. The neutrinos were generated at J-Park on the east coast of Japan in Tokai, and their properties were measured. The neutrinos moved through the central mountains of Japan and were measured again at the Super Kamiokande detector in Kamioka, 295 kilometers away. The data sets that were generated included very small files, less than a kilobyte in size, medium files that were up to 2 megabytes in size, and large files greater than 10 megabytes. All of the data had to be archived. Data sets were deposited into a repository at Keck in Tsukuba, Japan. The Keck repository was a tape archive. Tapes perform well when the file sizes are large. It takes about 5 seconds for a tape drive to spin up. Since the data write rate can be 100 megabytes per second, this implies the file size should be measured in gigabytes to amortize the startup time. The data set from the T2K experiment were way too small for efficient storage. The solution was to aggregate the files into a 2 gigabyte container, which might hold 100 to 100,000 files. The container could be written efficiently to tape. A data management system was needed to aggregate the files into the container and manage the storage. A similar problem occurs when moving data over large area networks. In this case, the latency is about 100 milliseconds for sending a single file. If a file size of 1 kilobyte is sent, the effective transfer rate is only 10 kilobytes per second. To fully utilize the network bandwidth, the files need to be aggregated into a gigabyte container before transmission. The T2K experiment presented a paper at the iRODS user group meeting on their use of the iRODS data grid to manage their experimental data. They used a staging area to aggregate files on a disk cache. When the total size was greater than a gigabyte, they created a tar container and stored the aggregated data in the tape archive. Since they did not want to lose any data, all files that were sent to the cache were also replicated to a second disk system. This meant that they had to manage not only the first cache, but also a secondary cache and a tape archive. Once the data were archived, they were deleted from the caches to make room for additional data. The approach was very successful, enabling a relatively small disk cache of 60 gigabytes to manage archiving of all of the experimental data. They wrote a bundle or replicate service that was executed periodically. The policy backed up all of the experimental data and controlled the amount of data on the staging area. The policy they implemented is shown here. The policy uses a microservice to find the size of the data on the cache, MSI check call size. If the size is above a threshold, a tar file is created and messages are written to a log file. A list of replica sites is generated, ACGET ICAT results, and the files are replicated to each site in the list. This approach made it easy to add new replica sites without having to modify the policy. Each step in the process is documented through writes to a log file.